Hope to see
Appreciate
you
it.
again in our future events. So we will have a quick quiz in the main room. So it will be 5 minutes, and we have some small prizes for the participants. So yeah, you can join the main room and then participate in the quiz. So we can slowly start. You can share your screen, Burak, if you want.
All right. Give me a second, please. Can you see my screen?
Yes, it is visible.
All right. Should we wait a bit more? Should we start?
You can start.
All right. Hi, everyone. Thank you for being here. I'm going to try to give some practical tips and tricks for a faster machine learning development lifecycle. Briefly about myself, my name is Burak. I am born and raised in Turkey. I studied in Istanbul Technical University. I studied computer science, then worked at a couple of companies in Turkey, namely started my career at a company called Pusmart. It was a digital marketing agency. Learned a bit about data and software in general there. Then I moved to Kolaibi. I think I was their first engineer. Then worked at Tazi, and after graduating, I moved to Berlin to work for this company called HelloFresh, where I was thinking I'm going to be here for a couple of years. I ended up being a little bit more than 5. And last year, I quit my job there to found Bruin together with my co-founder. I'll very quickly get it out of the way. What is Bruin? Bruin is a centralized platform that brings together data quality, data observability, data governance in a cohesive manner. A lot of the things I'm going to talk today are basically shaped out of our experiences throughout the years that we worked in industry, and they also ended up becoming inspiration for what we do at Bruin. Well, I'll start by saying that machine learning development is hard in general. You have to deal with a lot of different problems, a lot of uncertainty, and very little determinism throughout the whole every step along the way, basically. And this means that generally there's a lot of exploration, there's a lot of work teams need to do to figure out all of these problems themselves. If I were to try to group these problems to like, if I were to reduce them to a certain extent, I would start by saying that, okay, pulling and pushing data is very hard in general. You have to figure out a lot of stuff there. You usually deal with a lot of data. So it means that it requires certain engineering solutions. Along with that, there's often going to be a lot of code repetition. This means that across different models that are being built, we see a lot of teams repeating a lot of code and a lot of logic, trying to do the same thing over and over again. Alongside that, the machine learning workflow often starts from like a single Jupyter notebook, and then moves on from there, which means that there's going to be a single script that eventually starts doing everything and starts orchestrating every bit of the work that needs to be done for this model development. And throughout all of these, there's generally a major lack of observability. This means teams are sort of flying blind when it comes to building and operating their machine learning models, especially when they move on to production. This ends up being a machine learning model that is supposed to works on paper, but does pretty much not what you would expect. So I'll dig into each of these different problems and try to share some tips and tricks and some learnings that we've gathered along the way. And I'll start with the first one here now, which is pulling and pushing the data. Pulling and pushing data is generally a problem when you're working with machine learning models, because first of all, data is generally really big. It's going to be in the scale of gigabytes, if not petabytes of data. And this data often changes. There's going to be new events being added there. There's going to be a lot of new different types of data and new dimensions that you want to include in your models, new features you want to bring in. So that data tends to be hard to cache in general, both in terms of size as well as the nature of the data. In addition to that, pulling that data in to run in your models is generally costly, and the cost can be a direct financial cost in the form of egress fees. I don't know if you're familiar with the concept of an egress fee, but effectively it means your cloud platform is going to charge you money if you want to pull data out of their infrastructure. This is sort of like a weird, incredibly surprising way of locking people in. Still, I don't know how it is even legal at this point, but these fees are going to be they're going to get very expensive. And secondly, even if you didn't pay any money for that, you would still have to wait, because there's certain limitations with regards to your ability to pull data. Your bandwidth is going to be limited. You're going to have sort of problems along the way receiving this data, which means it's going to take you a long time to pull the data, as every time you want to change what you're doing and every time you want to update your model. On top of all these, even if you were to sort of figure out all of these different problems, deploying to production requires significant changes in your code. What do I mean by that? For instance, say you want to sort of bring data in from an external platform and have a tabular database running locally, and for that you want to use DuckDB to run things locally. And on production, you want to use your existing Snowflake data warehouse. This means effectively you're building two separate ways of working, two separate workflows that requires you to both repeat a lot of the logic, but more importantly, you need to maintain all of these, and going to production requires manual changes. So some of these are simple, some of these are harder as the data gets bigger, as well as the teams get bigger. Well, enter IBIS. So IBIS is an open source data frame library. It is effectively, so if you have used Pandas, IBIS should be very familiar to you. The guy that wrote Pandas is the one that wrote IBIS as well, so it's going to be pretty much the same. It is effectively, it allows you to use the same API and the same sort of domain-specific language, same way of dealing with the code and aggregations, but it supports various other backends. This means that, for instance, you can write a code that does a certain types of aggregations, and by the engine, by the backend that you pick, IBIS is able to either pull the data and do that aggregation locally, or convert that aggregation to a SQL statement and execute that against the data warehouse itself. This means for smaller data sets, you are able to very quickly iterate locally and build your aggregations and features and all of the calculations locally. Whereas when going to production, you can still rely on the capabilities of your remote engine, which often ends up being a query engine or a data warehouse. In practice, this means that throughout the same IBIS API, you are able to execute transformations across all of these different databases and data warehouses you see on the right, as well as regular Polars data frames, which are running these transformations in your computers. A very important practical advantage of this is working locally. It means that you can still use your local DuckDB, and without changing anything in your existing code, you can simply point IBIS to your Snowflake instance when you're going to production, which allows you to keep the same logic, go to production without changing anything along the way. This also has an important implication in terms of pulling and pushing that data, which is when you start pushing these aggregations towards the external, towards the remote data warehouses, towards query engines that are more capable, this means if you need a certain aggregation, you don't really have to pull all the data in, and instead let the query engine do its optimization, do the calculation where it lives close to the data, and then get only the resulting aggregation back, which reduces the time it takes to run these, as well as the cost in terms of pulling that data and processing that in your machine. And it also opens up a new set of possibilities, for instance, where you work with a data set that's like a huge, many gigabytes, hundreds of gigabytes. Maybe your computer is likely going to struggle quite a bit to do those aggregations, whereas platforms like BigQuery or Snowflake are effectively optimized for all of these use cases, which allows you to get the most out of that. By the way, I don't know if we are supposed to take any questions along the way. Are we gonna, like, shall we do it at the end?
At the end of the presentation, we can get the
All
question.
right, cool. All right, then I'll continue here. So effectively, relying on IBIS, you will end up building locally with smaller data sets and a faster iteration cycle without having to wait. You can also run the same code against large data sets through its remote execution capabilities, which means without changing the code, you get a different execution engine. So IBIS becomes like a major helper when it comes to dealing with pulling and pushing data. So let's put this one into green and then move on to our next problem, which is code repetition. Well, I think it's pretty self-explanatory. I'm sure all of you see this around as well, but notebooks repeat code everywhere. Notebooks actually push people towards a way of working where you sort of copy and paste and you move around, but this ends up making notebooks pretty hard to work with when it comes to production. In addition, you will often see feature generation and model training happening within the same file. And this means that every time you need to touch something, every time there is a common change that needs to, a different way of calculating a feature maybe, and you have a few different models, you're going to have to go through all of them, do the same fixes or same changes to all of these different models again and again, and it becomes a lot of effort. And an important side effect of these repetition across these models is it increases the cognitive load of the developer significantly. So when you're looking at the code, there's going to be this huge chunk of block that is being repeated everywhere, and it becomes a huge, very hard to maintain a mess, so to say. Yeah. So we start seeing code being repeated all around. It becomes the common practice. Every time someone needs to build like a new machine learning model, they're going to take a look at the old one, make a copy. So sort of like that, like 100 lines that is being copied starts becoming 200 lines, 500 lines, 1,000 lines. So every model copies the same logic over and over again, even for the basic sort of feature engineering and data aggregations. Well, the solution that we often see being applied here is shifting these responsibilities towards the left. What does shift left mean? If you think about the machine learning development itself as a pipeline, so you have raw data at some point, you have sometimes clean data along this way, and then you get this data into your working environment, you start calculating sort of some features for your models themselves. Then you do a model training, and then you sort of analyze that model. You see if that does what you expect it to do, and maybe iterate on that a couple of times, which eventually then ideally goes to production. It doesn't just stay in a notebook. The principle of shifting left means if you consider this as a pipeline that goes from left to right, some of these responsibilities could go further towards the left, further towards the beginning of the pipeline, which allows standardizing a lot of these different bits. So for instance, feature calculations are pretty sort of generalizable way of working with machine learning models, which means if you have certain set of features that you need across different models, you might as well calculate these before there is any model work being included in your data pipelines. This allows you to standardize some of these logic and feature generation step, but also allows you to get some of the further advantages from the regular, like other parts of the software development lifecycle. Shifting left has like a couple of benefits here. So it allows you to have much better observability within this rest of the pipeline, which allows you to see, okay, where am I getting this data? What do I use it to calculate this specific feature, etc. And compared to working in a notebook, you will often have these as a hidden dependency where you need to dive deeper into the code to understand what it is actually doing and where is it getting this data from, etc. It also allows you to enforce much tighter data quality standards. So this means that every step along the way, as you ingest data, as you clean the data, as you start calculating features, you can enforce data quality every step along the way. This means that you don't have to do same error checkings. You don't have to do same sanity checks in every notebook every time you want to execute, which can be costly both in terms of financial impact as well as the time, but you can instead make it a part of your existing data pipeline. And in the long run, this ends up being a more maintainable way of building software in our experience, which is effectively allows treating these individual data assets as regular software as well and applying the same principles there. What do I mean by that? Your feature engineering code will be versioned, it will be tested, it will be deployed, it will be executed, it will have alerts on that. So this allows you to generating those features in a production level even before any machine learning starts, which allows you to then focus on the ML development part without having to think of, oh, did I calculate this feature correctly? And it also allows you to centralize a lot of this logic, which means it's much easier to maintain. Talking about the shifting left here, I want to quickly mention entity-centric modeling. It's effectively well, I have an example here. Yes. So it's effectively the idea that your business probably has a set of core entities that you build your user workflows, your machine learning models, etc. Around of. And this means that you already have these concepts, you have these entities that everyone is operating around. Your data workloads can operate around them as well. In practice, this means that you would have a table with certain features for every dimension and breakdown you want to take a look. For instance, for users, you would have a table for user features. For product, you would have a table for product features. And sometimes you're going to have a combination of these, like a user product features where you have certain calculations on a breakdown by user and the product itself. This means if anyone needs to have access to any user level features, user level metrics, they know where to go, they know how to access this metrics, and it makes the general navigation very easy. In the case that the general data warehouse gets bigger, as you would imagine, as the size of the data grows, as the company grows, different business teams grow, you are also able to split some of these tables by domains, by different products, by different owners if necessary. And here's an example for search being a domain here, where you could have a user level feature set specific to search here, which you can expose to the rest of the organization, which allows you to keep the feature calculation logic within a domain without having to pass it all around, while also still having that reliability of everything, building all of these in the earlier point in the data pipeline. I left an interesting article here with regards to entity-centric modeling. We have seen this being applied to a great extent, so this is definitely would be a good read on the topic itself. I want to quickly touch about another aspect of this life cycle here, and maybe share a bit more few conveniences here. So when we are working with a machine learning model, we're often going to be at a point in time where we have certain data that we train and test our models on, and then we're going to have like a different cutoff in our data that allows us to sort of validate our models and do a back testing to see how things would change if we were to rely on the business metrics. Then often what we recommend is, look, now you can release your model in the wild, and then your training and test data, all of them becomes exactly from before. You don't need to do like any additional validation split there. And then you can roll out your machine learning model as part of an A/B test here to see how the user behavior shifts, how different product level metrics shift. But often you want to be able to run your machine learning model or get a set of features for a specific point in time to be able to simulate how would the model behave if we were running this a month ago from now. This often means that you want to shift that now line across further in the past, and it requires a lot of repetitive code to be written to handle dates flexibly. I think I even have an example. Yeah. So for instance, if you needed to do a couple of metrics that need to be calculated for between a specific start date and end date, you would have to first calculate those dates with the delta that you want to have, and then build a string templated query, so to say, that allows you to inject those dates and then run that query against your data warehouse. This means everywhere, every model, every time you need to do time traveling in your existing metrics, it would require you to copy the same logic over there and repeat all of these, which ends up again being repetitive code. A nice way to avoid this overall problem is user-defined table functions. So pretty much every major data warehouse that I know supports table functions, which allows you to say, hey, I have this logic that I want to sort of filter data ahead of time and gather certain events by certain date or certain metrics by certain date. I could actually define these this table function inside the data warehouse itself, which allows us to remove this logic from our individual models and instead centralize it inside our data warehouse. This means that in practice, you would create the table function that we see above in this page only once in your data warehouse, and then your scripts become much easier to they become much simpler. You don't need to do all of that string slicing and sort of additional things that you need to do there. And another benefit of this is now you're able to do the same thing in your data warehouse as well, which means if you were, let's say, on Snowflake UI or BigQuery UI, you are able to get the data as your model sees as well without having to do manual work of rebuilding that script over and over again for yourself. Well, we talked a bit about the code repetition in general, so I'll mark that one as green. Let's go on to scripts being used as orchestration engines. We often see, and I think, again, this is part of like a notebook workflow, which means we see a lot of scripts that tend to create tens of tables and doing multiple jobs of, okay, talking to external APIs, getting data from the databases, getting data from data warehouse, doing a bunch of pre-aggregations and creating and updating tables in the data warehouse. And this script becomes the thing that does everything else. This means that within this, it is like a poor man's orchestration, effectively, meaning that you're going to have to write this orchestration step in code by yourself, and you're limited by the general linear execution capabilities here. You lose the lineage of every bit of data that you calculate here. it becomes very hard to retry from a failure when you are running this full script on production. Let's say you have 5 different steps and a third one failed. You often have to run the whole thing again and again, which introduces a lot of inconveniences in the process. And it becomes very hard to parallelize in general, which means, let's say I need to have 3 tables being updated with different set of metrics that we calculate along the way. I have to take care of the whole, like, how do I parallelize this question in my scripts myself, which is often a lot of work. And I'm sure some of you have used the multiprocessing libraries in Python, which are not the most fun ones to deal with. And in the end, it makes the whole thing very complicated, especially when someone new joins the team. It becomes very hard to share what's happening here and very hard to understand for ourselves as well. Well, the solution here tends to be rather obvious. This is a known problem. There are proper orchestrators that you can use to orchestrate these different parts of your workflow, which means that, kind of like in a similar sense of shifting left all of these responsibilities, you can actually push a lot of the complexity into the orchestrators themselves. I've left a couple of orchestrator examples here, but there's like a billion of them. One of them is my company, shameless plug, but it's effectively, you could use any of these that would make your life much easier than having like a single script doing all of these. This means, since the orchestrator has native understanding of what is a specific task or a data asset, it becomes much easier to debug when something goes wrong. It allows you to identify issues very quickly and also fix some of these problems very quickly. So it means this sort of becomes your backbone of your data pipeline, which reduces a lot of these complexity and makes it the tool's problem, which is it is specialized to solve this. I've left an example of how that sort of web of dependencies would look down here. In practice, when you start running some of these workloads, you're going to start having certain parts being updated automatically in parallel, certain parts that need to be updated after table A and table B is modified, etc. And you want your orchestration tool to be able to handle pretty much all of these. But here, I think there's a good example where a specific model failed in this process, which often it will, and you have a solid visibility into what failed where. And you can retry only that one. You can define custom retry policies across all of these different aggregations or calculations that you run. And effectively, when you want to renew this failed model, you don't have to touch anything else in the rest of your data architecture unless they depend on this specific one, which makes the overall operation much easier than, well, okay, I have this 15 notebooks that I need to run again and again, and sometimes even maybe a specific order. So briefly touch the scripts as the orchestration matter, and that takes me to my sort of rather final matter, which is the general lack of observability across machine learning development. What do I mean by that? When you are working on a machine learning pipeline, there's often going to be the question where you say, okay, am I using the correct data? Did the model refresh itself last night? It was supposed to get the new data and renew, like either retrain or do certain batch predictions when it was supposed to do. How does the accuracy of the data change over time? Does the model perform properly? Do we know what it's doing? If you were running a specific A/B tests, do we know what metrics are being affected as a result of a specific A/B test? Do we know how do they change? How do they shift, etc.? So this sort of questions around observability puts a lot of shade on the overall the success of machine learning projects internally and pretty much every company, and they become a major source of trouble for every team to build these workflows by themselves. And in the end, we noticed that data quality tends to be a major issue for all of these machine learning models, because in the end, if you have bad data, you're going to have bad models, which means they're going to have bad predictions. They're not going to perform the way that you want them to, even though you had all the data correct. This graphic on the right side it sounds silly, but you'd be surprised how often we see the same kind of problems being repeated everywhere, because that data tends to be not in a standardized format, which means often your models are not aware of what's happening actually, and you simply deploy something and go to production. This means that you need to ensure data quality sort of is a first-class citizen before you build any data models. It requires you to automate your data quality checking at every step along the way. And along these, it should unlock you to check the business metrics that you would normally look at. If there was like a business team that would look at the data, what questions would they ask? And allows you to validate all of those assumptions before any machine learning model is even involved in this process, sort of, again, in the principle of shifting left that responsibility. It also allows you to, it should allow you to write sort of custom logics when you are checking the quality of the data. For instance, if you have a machine learning model that you want to trigger, you want to run based on a pre-aggregated revenue data, you almost always want to make sure that this revenue number is accurate, it's not duplicated. And a good example of ensuring that is if I have an external separate transactions table, I could simply compare the numbers for the last day or the last 7 days or the last 30 days and see if the aggregation that I was supposed to have is actually there, or if it's within the ballpark that I expect, which is, I don't know, the revenue could be maybe less than 5% of what we see, including the refunds. But if it's any more below than 20%, I really don't want to train my model on this. I really don't want to do any prediction because there's something fundamentally broken here. An important thing to understand in this logic, though, is data quality and observability is very much cultural rather than a tool-driven problem. Of all of these plus some long-running practices that allows you to get better at in machine learning itself. And it also, you need to accept the fact that it's going to be a long journey. You constantly iterate on all of these different aspects rather than having a single thing that ticks all the boxes, and then it becomes like this magic new world where you can do ML without thinking about all of these. That would be it. So thank you very much for being here and listening to me. If any of these things sound interesting from a product perspective to solve some of these problems and to enable people, we are hiring. We're looking for engineers to join our team, product people to join our team, etc. Or generally, it could be the case that we don't have an open role, but you think you would be a good fit. Please do reach out to me. I left some ugly looking QR codes here that you can use to go to our jobs websites, but always feel free to drop me a message on LinkedIn as well. I try to be very responsive there. And yeah, I guess that's pretty much about it. Thank you for listening to me.
Thank you so much for your great talk, Burak. So if any question, we can get the questions if anyone has from chat, or you can raise your hand. If not, maybe I can ask a question.
Please.
So actually, I am currently working on a project. We are working on a Databricks. So you talked about the shifting left principle. I guess I like it very much if there's something you calculate in the model development, just put it into the data pipelines.
Yeah.
In Databricks, as far as I understand, they are pushing, I guess for now, we are implementing the pipelines in some of them in the notebooks. Is this a good practice? What do you think? Or in the notebooks, should we only develop the models and everything that for the data pipelines should be in the Python scripts? Right.
Look, I'm rather opinionated on how to work and how to build some of these workflows. So take it with a grain of salt, okay? There's no one single answer. But often if I see any business logic being calculated in notebooks, that smells. That's called smell for me. That means that I would expect those business logic to be extracted outside of the notebooks themselves, not because notebook is a bad technology, but more because notebooks are very hard to productionize. They tend to have a completely different way of working than regular software engineering practices. That's why we would instead recommend, look, move things to outside of your notebooks, do some of these calculations, actually push these calculations to be in SQL as much as possible if your data warehouse supports that. If not, do it in Python, but this time treat it as a proper software asset, proper piece of software, which means version control them, which means apply testing to them, apply certain governance rules around ownership of them, apply alerts on these calculations. These are things that are very hard to do when you're dealing with a notebook, because it is essentially meant to be an interactive development environment rather than a production piece of software. I think the same question could be asked, what would you think if someone was building an API with a notebook? You know, if your notebook was running as an API, I don't think anyone would like to do that. We probably should not do the same with our feature engineering and any sort of logic that could live on our pipelines. You know, in the end, the pipeline is there to take care of some of these problems. You know, you might as well use the tool and rely on that. And like, look, any platform, I think like Databricks has workflow orchestration, Snowflake there's Airflow, Daxter, we do that. There's like a billion different ways of doing the same thing. I think across, if we were to list all of them, doing them in the notebook would probably get somewhere at the bottom. You know, so if you see something that you often do, if you see an important metrics, pull them out of the notebook, productionize them. You know, that allows you to move much faster when things change in your models, when you test new models, etc. In the end, when I was leading my team at HelloFresh, one of the core things we focused was we need to iterate fast. You know, it's not important that we get the best thing out there today, but we need to be able to iterate very quickly. And I think these practices allow data teams to iterate much faster in a much more effective way as well.
Got it. Yeah, it makes sense. Yeah, to moving to business logic completely out of the notebooks so that easier to test.
Yeah.
Okay, so I guess it looks there's no other question. Thank you again for your great talk, Burak.